Good morning, everyone. Today, we delve into the fascinating world of statistics, specifically a concept that underpins countless analysis, the Norman distribution, also fondly known as the bell curve. Imagine a giant bell, not the kind you ring, but a smooth, symmetrical curve. The curve represents the Norman distribution, where data points cluster around the central point, the mean, and gradually taper off towards the extremes. The beauty of the Norman distribution lies in its predictability. Most data points, around 68%, fall within one standard deviation of the mean. Standard deviation, a statistical sidekick, measures how spread out the data is. As we move further away from the mean, the frequency of data points dips. By two standard deviations, we encompass roughly 95% of the data, and by three, a whopping 99.7%. This predictability makes the Norman distribution a powerhouse in countless fields. Imagine analyzing test scores. The average student, the mean, is surrounded by those who score slightly higher or lower within one standard deviation. Scores on the fringes, very high or low, become increasingly rare. The Norman distribution finds use in everything from predicting heights and weights to analyzing stock market fluctuations. It helps us understand natural phenomena like wind speeds or rainfall patterns. By studying deviations from the Norman curve, scientists can identify outliers, potential issues that demand further investigation. The real world and the not so Norman curve. While the Norman distribution is incredibly useful, it's important to remember it's a model, not an absolute truth. The real world can present messy datasets that defy the bell curve's perfect symmetry. For instance, imagine analyzing house prices in a specific neighborhood. There might be a cluster around the average price, but a luxurious mansion on the top of the hill and the fixed upper on the outskirts could skew the distribution. This is where statisticians employ a toolbox of techniques to analyze non-normal data. They might transform the data or use specialized statistical tests to draw meaningful conclusions. The Norman distribution in action. Let's bring the Norman distribution to life with an example. Imagine a factory producing light bulbs. Ideally, all bulbs would last exactly 10,000 hours, which is the mean. The Norman distribution tells us that some bulbs might burn slightly brighter, with lasting a bit longer, or dimmer, burning out sooner, following a bell curve around the average lifespan. By monitoring this distribution, the factory can identify potential issues. An unexpected shift towards shorter lifespans might indicate a faulty production batch. The Norman distribution thus becomes a valuable tool for quality control and process improvement. The future of the bell curve. The Norman distribution remains a fundamental concept in statistics, but the world of data analysis is constantly evolving. With the rise of big data and complex data sets, statisticians are increasingly utilizing more sophisticated techniques. However, the core principles of the Norman distribution, understanding central tendencies, and the spread of data will continue to be valuable tools for making sense of our ever growing data driven world. Beyond the bell curve. It's important to remember that not every dataset follows a normal distribution. Incomes, for example, often skew towards the lower end, with a few outliers at the high end. This is called a skewed distribution. The language of the bell curve. The Norman distribution empowers us with a specialized vocabulary. We can talk about the area under the curve to represent the probability of a certain outcome. We can calculate z-scores, a way to express how many standard deviations a specific data point is from the mean. The takeaway. While the Norman distribution might seem like a simple bell curve, it unlocks a powerful way to understand and analyze data. It helps us make sense of the world around us, from the predictable to the exceptional. Further exploration. This is just a glimpse into the vast world of Norman distribution. If you are curious to learn more, you can explore concepts like standard deviation, z-scores, and skewed distribution. There's a whole world of data waiting to be unveiled. The central limit theorem, a powerful ally. The Norman distribution significance is amplified by a cornerstone of statistics, the central limit theorem. Imagine you repeatedly flip a fair coin and take the average number of heads across multiple pairs. Surprisingly, the distribution of these averages, regardless of the initial number of flips, tends towards a normal curve as the number of flips increases. This magical property applies to many scenarios where random variables are averaged. For instance, the weights of individual apples might vary, but the average weight of apples from a large orchard will likely follow a normal distribution. The central limit theorem empowers us to use the normal distribution even when the underlying data itself isn't perfectly normal. Think of the Norman distribution as a statistical hero. It tackles a wide range of problems, from analyzing exam scores to predicting customer behavior. Its ability to model symmetrical data and predict probabilities makes it a go to tool for countless analysis. However, like any superhero, it has limitations. The Norman distribution struggles with skewed data or data with extreme outliers. In such cases, statisticians employ alternative distributions or transformations to bring the data closer to the bell curve's form. Understanding these limitations ensures we use the normal distribution appropriately and effectively. The Norman distribution serves as a springboard for delving deeper into the fascinating world of statistics. By mastering this fundamental concept, you unlock the potential to explore more complex distributions like the t distribution or the chi square distribution. These specialized distributions cater to specific scenarios where the Norman distribution falls short. The journey from the bell curve to these more intricate distributions empowers you to tackle an even wider range of data analysis problems, equipping you to extract valuable insights from the ever growing ocean of data surrounding us. The history roots of the bell curve. The concept of the normal distribution has a rich history. While its applications explored in the 20th century, the seeds were sown much earlier. In the 18th century, mathematicians like Abraham de Moivre and Pierre Simon Laplace laid the groundwork with their work on probability theory. Later, mathematicians like Carl Friedrich Gauss further refined the concept, and the now ubiquitous bell curve shape emerged. Interestingly, the Norman distribution found early applications in astronomy, with applications in describing the distribution of errors in celestial measurements. The Norman distribution empowers us to move beyond simple averages. Standard deviation, as mentioned earlier, quantifies the spread of data around the mean. Think of it as a measure of how clumped the data is around the average. A low standard deviation indicates a tight cluster, while a high standard deviation suggests a more spread out distribution. Furthermore, the five number summary minimum, maximum, median, the quartiles di- that is dividing the data into four equal parts provides a more comprehensive picture of the data's distribution compared to just the mean. The Norman distribution plays a crucial role in hypothesis testing, a fundamental statistical technique. Imagine a researcher investigating whether a new fertilizer increases plant growth by comparing the average growth of plants with and without the fertilizer and assuming the underlying data follows a normal distribution. The researcher can statistically assess the likelihood that the observed difference is due to chance alone. This allows for drawing conclusions about the effectiveness of the fertilizer with a degree of certainty. Visualizing data is key to understanding its distribution. Histograms, bar charts that depict the frequency of data points within specific ranges, are ideal for portraying the curve shape of a normal distribution. Additionally, software tools allow for generating probability density functions, which are called PDFs for short. Smooth curves that depict the theoretical distribution of data points under the normal curve assumption. These visualizations help us interpret data patterns and identify potential deviations from normal. The normal distribution equips us with a specialized language for discussing data. We can talk about percentiles, the percentage of data points falling below a specific value. We can calculate z-scores mentioned earlier to express how many standard deviations a data point is from the mean. This standardized language allows for comparing data points across different data sets, even if measured in different units. Thank you very much.